and experience the essence and majesty and dynamics of AP chemistry. Okay, so on that assignment that I just gave back, this also plays out into some stuff we're going to do today. Okay, let's say you have, I don't know, silver carbonate, Ag2CO3, okay? And this is just annoying. Some of you put brackets around there and left it there. You only put brackets around a polyatomic ion if you have more than one of them, okay? Don't put the brackets there unless you're going to put a subscript on the outside, okay? Stop. Don't. Okay. With that said. Now, here's the bigger idea. So let's talk about that assignment from yesterday. So, kind of 53 summarizes a whole bunch of things. Let's talk about 53. So, and some of you have already experienced this. If you come up and you say, Mr. Burkamp, I don't know how to do 53. Here's the first question I'm going to ask you. Have you drawn a rice chart? And if you say no, I'm not going to help you. And I'm not doing that to be a jerk. Because if you don't know what the reaction is, if you don't know what the initial conditions are, you're shooting in the dark. Okay, you cannot solve the problem. And so the whole purpose of the rice chart is that it keeps you organized. Yes?
Are we going to get counted off if we don't have a rice chart?
Well, no, but if your answer's wrong and I can't track what you did,
okay.
I'm telling you right now, I'm not sorting through random numbers. Okay? So, on all of these aren't reactions with acid bases. All of these are ionizations of acids. So, all of these are going to start off with, and here's the shortcut version, HA turning into hydronium ions and anions. Now, implied within this is water molecules, okay? This is a tug of war between the acid itself and its attraction for the water molecules, okay? So and this is the huge contrast. If it's a strong acid, you're going to prom as just friends. You're going to go there long enough to get to prom, and then you're going to ionize, okay? You are not going to stay together as the molecular form of a sedate. If it's a weak acid, and here's the dichotomy, the weaker the acid, the stronger the bond between the hydrogen and the anion. Because remember, Mother Nature is a lazy prima donna. Mother Nature is going to remain in whatever the most stable form that it can possibly exist in. So that's going to be the main difference. So let's say, for example, if you look on 53, this is going to be a weak acid, so here's this molarity. We're not neutralizing this, we're not reacting it with a hydroxide, nothing. So unless you're explicitly told differently, that initial condition is going to be, there's your acid, you assume that there's no hydronium ions and there's no anions. You have made your grand entrance into prom. You haven't ionized yet, you're here at point 1, okay? Now, here's the difference. If this is a strong acid, all of that would ionize, so your change is going to be what's going to happen. Okay, what happens when you get to prom? If it's a strong acid, all of that's going to go away. Okay, and you will not have any of the molecular form, or at least a tiny, tiny, tiny bit of that molecular form existing in that solution. Because basically what's happened is this. Here's Joe water molecule. Hydrogen N, negative N. The attraction between that hydrogen and that anion is stronger for the water than it is for the molecular form of the acid. When you go to prom, you are more attracted to your friends than you are to your date, and you're going to ionize. Okay? So if this is a strong acid, all of that would ionize, okay? And this would become 0.1, and this would become 0.1. Now, this is one of the questions. This is why you do not find Ka values of strong acids. Because if you look at how Ka is calculated, and I cannot emphasize this enough, when you see an uppercase K, no matter what it is, that only exists at equilibrium. That is when Mother Nature is most laid back, chilled out, smoking on the hookah pipe. That's when she is most chilled out, and that's how Mother Nature wants to be. She wants to be completely chilled out. So if you look at how you calculate Ka, and don't discount the mathematics of this, so anion concentration divided by HA. The whole key to this, that is not the initial conditions, it is not the change, it is only the equilibrium line. So if this was a strong acid, this would be 0.1, that would be 0.1, and that initial concentration on that acid at that equilibrium is going to be 0, or at least a very, 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 very small number. So that means Ka values are either, for strong acids, are either undefined, because you're dividing by 0, or they're extremely large numbers. So one of the things that you will see as we progress through this journey, we're going to talk about Ka, we're going to be talking about Kb, we're going to be talking about Ksp, okay? So anytime a K value is less than 1, and the smaller it is, that means the less favored the forward reaction is. If Ks are really, really big numbers, that means the forward reaction is very favorable. So if you look at the chart of Ka values, notice that they're all really, 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 really small numbers. 10 to the negative 4th, 10 to the negative 10th. Because the forward reaction isn't favorable. Later on, you'll see how that fits with the concept of what's called Gibbs free energy. Okay? We'll be talking about spontaneity. There's a whole bunch of things that will eventually fit into a big puzzle. So this is just piece number 1 of a puzzle. Okay? But here's what I want you to understand. If you have small K values, no matter what it is, the forward reaction isn't favored. So this is why, don't come up and you say, hey, I can't find the Ka value of nitric acid. You know why? It doesn't exist. Because there is no K value, because it's either undefined or really, really big. Now, one of the questions on your assignment is even with sulfuric acid, H2SO4. Okay, H2SO4 is what's known as a diprotic acid because there's 2 hydrogens. Sometimes you get triprotic acids like phosphoric acid, which is H3PO4. And so one of the questions is, why is there not a Ka value for H2SO4, but there is for HSO4? Okay, so and again, this is a bigger picture. So this goes in stages, okay? The first ionization is this, HSO4, 1 minus. So basically what happens is that you have this molecular form, you have 2 hydrogens and an SO4 sulfate. So basically the first hydrogen goes away very easily, okay? This is why it's defined as a strong acid. So if you were to try and calculate the Ka of this, it would be that hydronium ion times your HSO4 divided by the concentration of your H2SO4 at equilibrium. There is no molecular form of the H2SO4. It's 0. You're dividing by 0. It becomes undefined. So this is why when you look on your chart, okay, there is no Ka value for H2SO4 because it's undefined, because you're dividing by 0, because there's no molecular form of it, because that's what makes it a strong acid. Now, in the second stage of the ionization, you're going to start with HSO4 minus, and that's going to break up into H plus, and then SO4 2 minus. Now, if you look on your table, you can find a Ka value, and it's called Ka2. Clever, because it's the second hydrogen. That's why it's under the Ka2 column. Okay? Vanessa, I want you to know that I swear to God, without my glasses, it's like I'm teaching my mom. So, it's just disturbing.
I guess that's what I was going for.
Oh my God, it's just, anyway. Okay. If I have nightmares tonight, I swear to God. Anyway, if you get an email like 2 o'clock in the morning.
No one else stressed out.
I admire your spirit.
Oh, is it homecoming week?
Okay.
Yeah.
So now, when you look at this Ka value, so the second ionization of sulfuric acid is a weak acid. okay? And here's the reason why. You can find a Ka value listed, because again, that's going to be that hydronium times that SO4 2 minus divided by the SO4 concentration. Okay, cool with this. So you can find that value. Now, look at that number. Jamie, look at that value.
Where?
For on who's ever got their book open on that index chart, where it's got that the chart of all the Ka values. What's the value for sulfuric acid for Ka2?
1.2 times 10 to the negative second.
Now, notice for Ka values, that's actually a pretty big number, okay? It's 10 to the negative second. Relatively big number compared to the other ones, because some of those are 10 to the negative 6, negative 10, whatever. So, even though this is a weak acid, this will make sense. It's a strong weak acid, okay? So in other words, you got 1.2 times 10 to the minus second. Now, here's the other thing that you have to keep in mind. Mother Nature is going to do whatever Mother Nature has to do.
It's just my shirts.
Okay. Mother Nature is going to do whatever Mother Nature has to do to get this number, okay? That's going to be your overarching theme later on. Mother Nature wants this number. So mathematically, whatever happens here is going to get you this number. Okay, this is going to play out when we get into buffered solutions, a whole bunch of things. It's a simple concept, but if you remember, Mother Nature wants to be in equilibrium. She wants to be chilled out, hitting that hookah pipe hard. She wants to hit that hookah pipe. Okay? She doesn't want to have to be wandering around trying to keep things in equilibrium. She wants to be in equilibrium. She wants this number. So whatever has to happen here, she's going to get to this number. Okay? Got that concept? Okay. Now, circling back all the way to question number 53. Okay? So in 53, you're told that this thing ionizes at 11%. Now, here's the significance of that 11%. There's something known as the 5% rule. If your ionization is less than 5%, what we're assuming is that when we subtract that amount of ionization from the initial concentration, it's not enough to change significantly your equilibrium. But since this is 11%, that's well above that number, which means when you subtract it, now it becomes significant. So that's like taking a spoonful of water out of a cup, okay? That's significant. But if I take a spoonful of water out of Cheney Lake, it's not going to make any difference. In both situations, you take a spoonful of water out, the question being, it doesn't make any difference in the grander scheme of things. So since it's 11%, that means it's significant. Now, 11, what we're saying is that 11% of 0.1 is going to ionize. You do the math, that becomes 0.011. That's my change line. This is how much of that concentration is going to ionize. That's 0.011. Now, here's the other thing that's important when you get to 53. You're trying to find the Ka value, okay? So here's the contrast to what's happened before. Before, you've been given the Ka values. And by the way, that's what's going to happen on the quiz tomorrow. I promise you there's going to be a weak acid calculation on the quiz tomorrow. Okay, promise you. I'm going to give you the Ka value, okay? And you have to figure out what the concentration of the anions are and the pH and all that type of thing, okay? Promise you there's going to be just one problem like that. There's going to be some question on like redox, no redox, no percent compositions, no 4 of the strong acids, and the formulas. Okay, so here's what's going to be important. I'm going to lose some of that acid. Okay, again, because it's a 1-to-1 ratio, whatever I lose here, which is going to get subtracted, is going to get added over here. Okay, because it's a 1-to-1 ratio. Don't have to think, it's just boom, whatever that is. So when you subtract that out, that becomes 0.089, that becomes 0.011, that becomes 0.011. So now, when you do that Ka calculation, and you've got to keep this in mind, That K, because it's talking about equilibrium, you're going to put in the equilibrium values, not the change, not the initial. You're going to put in the equilibrium values. So basically, this is going to become 0.011. That's going to be 0.011. That's going to be 0.089. Okay? Now, word of advice on rounding. Don't round until you get to the end. You want to keep more digits than what you need, and then round when you get to the end. Now, pH is a little quirky when it comes to significant digits, and I know you all learned that in Chem 2 or at some point. When pH has its own set of rules when you're talking about significant digits. Like, let's say, for example, your pH is 13.50. With pH, the significant digits are only the numbers to the right of the decimal place. So when you see a pH of 13.50, even though it looks like there's 4 digits, that's actually only 2 digits, because we assume that there's no uncertainty in the 13. The uncertainty comes with the decimal places, and all of your pH probes are going to measure out to 2 decimal places. So whenever you express pH, 2 decimal places to the right. Okay, it's an absolute rule. Just even if there's zeros, you got to put, like, if it's exactly like neutral solution, you have to put a pH of 7.00. Okay. All right. So anyway, so on 53, you should have 4 answers. Okay. So here's your sheet of paper, and what I want. So here's going to be 53. I want 4 distinct answers, and just do not write down numbers and think that, oh, Burkamp will know what they mean. No, Burkamp won't know what they mean, okay? But if Burkamp was good at predicting numbers, I would have won the jackpot by now. Helps if you play, but that's a whole other story. So what you should see on 53 is there's 4 answers. Your anion concentration, your hydronium ion concentration, the concentration of the acid, and the Ka value, okay? So on 53, you're going to say, oh, here's my anion concentration. Here's my acid concentration. Here's my Ha. Here's my Ka. Okay? I want all 4 answers clearly labeled. I'm not going to guess what they are. Okay? Horrible at that. Lay those out so I know that. But here's the bigger idea. Okay? When you get to this level of science, whether it's physics, chemistry, whatever, you have to remember, you have to get out of this mindset that, well, I got the answer. I don't care. Okay? I don't care. If the work that you show doesn't generate that and I can clearly follow it, I don't care. Okay? You do the process, the product will take care of itself. You have to get out of this mindset. I randomly punched numbers into a calculator, a miracle happened, and I got the right answer. That dog is not going to hunt. Okay? You have to show the process. And the reason I do that isn't to be a jerk, okay? It's because that's how it's done. You look at my answer keys. I have rice charts on every one of these, okay? Every one of these. You look at what I did, every one of these has a rice chart because it works. It keeps your thought process organized. Okay, so let's talk about 62. So on 62, because if this number is wrong, everything else is going to be wrong. So on 62, the first thing you have to figure out is the concentration of the acid itself, which should involve a lot of 2's. Okay? So that initial concentration should be like 0.0222 molar. What?
Could you walk through how to solve it? Because I don't know how you would solve it.
Okay. So you got 1,000 milligrams, right? There's those ones are 2 500 milligram tablets. Okay, in terms of how I got that molarity or the next step?
Just like, I don't even know how to start it.
Okay. So you got a total of 1,000 milligrams, right?
Yeah.
So there's 1,000 milligrams in 1 gram. So at the end of the day, molarity is moles per liter. So you got to calculate the molar mass of, I don't even remember whatever that substance is. It's like 180 grams per 1 mole, and then it's dissolved in 250 milliliters. So this is, again, let the units lead you to the promised land. Because if you just randomly write down numbers and hope that a miracle happens, no, Christmas is past. The season for miracles is not happening, okay? Let the units lead you to the promised land. So you do all this, that becomes the molarity. Okay, because if that's wrong, literally everything else is going to be wrong. Okay? Now, here's the deal. So this is just an ionization, hydrogen, your anions. So this is starting off at 0.022. This isn't what we call a buffered solution. We'll get into buffered solutions later. So this is 0, that's 0. Now, in this situation, you know what the Ka value is. Okay? So this is going to be minus x plus x plus x. This becomes 0.022 minus x, x, and x. So in this situation, and I'm not going to expect you to do this on the test. I'm not going to expect you, and the AP never has questions like this where you actually have to work it as a quadratic. But I want you to see the significance of this. So that Ka value, which is 3.3 times 10 to the negative fourth, is going to equal the hydrogen ion concentration, which is going to be x, the anion concentration, which is going to be x, and then 0.022 minus x. So this is the only time you've got to work this as a quadratic. And the reason that we have to do that is because this subtraction of x is big enough that it alters that significantly, it alters that value at the equilibrium. Most of the time, like on the quiz tomorrow, when you subtract x, it's not going to make any difference, okay? So on the quiz tomorrow, you're going to start a problem just like this, but you can just leave that concentration as that number. You don't have to worry about subtracting the x. I just want you to be exposed to this and go, wow, sometimes this is significant. And most of the time it's not, because it's such a small value, because it ionizes so small. This particular situation, it actually impacts what you do. So, remember the quadratic, negative b plus or minus square root of minus 4ac all over 2a. You're going to get two possible roots. One will make sense, one won't. So if you, once you solve for x, you should get a GPA times 10 to the negative third. So when you go through that quadratic, you should get a GPA times 10 to the negative third. And then you're going to take the negative log of that. So on 62, that pH should be around 2.6. Should end up somewhere around there. Now, let's talk about 56, because 56 algebraically is a little bit tough. So on 56, you have hydrofluoric acid. And remember, hydrofluoric acid is the only acid where it has a halogen that's a weak acid. All the other ones are strongs. So here's the deal. When you set up this rice chart on 56, what you're trying to find is the initial concentration of the hydrofluoric acid. That's your unknown, okay? You're trying to find the initial concentration. Then you go 0, 0. Now, they gave you the pH of 3.65. Once you know the pH of 3.65, then you can figure out the concentration of your hydrogen and the concentration of your fluoride. So, you do that, you get 2.239 times 10 to the negative fourth. That's 2.239 times 10 to the negative fourth. And that's 2.239 times 10 to the negative fourth. So this becomes x minus that number, you know the Ka value, solve for x, and you should get something times 10 to the negative fourth as your answer. So, there you go. anything else, what you should see, by the way, on number 15, you should see that those ionizations are getting higher and higher and higher, okay? And you should see that the pH is also getting higher and higher and higher. Because what's happening fundamentally is that that solution is becoming more and more dilute. So here's one way you can kind of visualize what's happening on 15. You can imagine it being like the hallway, and we'll use this analogy later on as well, a couple of different times. So if you look at what's happening on 15, your concentration is becoming smaller and smaller and smaller and smaller and smaller. So what that means is, if you want to think about it this way, it's easier, like imagine that you're going out into the hallway. You're going to ionize from this class, and you're going to go out into the hallway. Well, if the hallway is really crowded, then it's harder for you to ionize, okay? But if the hallway is empty, then it's easier for you to go out into the hallway. It's easier for you to break free. So what's happening conceptually on 15, as you become more and more and more dilute, it's easier for those molecular form of those acid to ionize. The other way that you can think of it conceptually is that you're becoming closer and closer to neutral water. Well, the pH of neutral water is 7, okay? So as you make this more and more and more and more dilute, it's becoming more and more and more like water, and so that's why that pH is also going up, okay? So if you want to think of it that way. Let me see. On number 6, your hydronium ion concentration should be something times 10 to the negative 4th. On 7, your pH and pOH should be around 7. That's an ish. Okay? Your pH and your pOH should be around 7. On number 14, your hydronium ion concentration should be something times 10 to the negative 4th. Because if that's right, everything else will probably be okay. All right. Anything else you want me to go over? Yes?
Can you help me conceptualize number 8?
Was that the question, like with the molarity in the bottles?
Yes.
Okay. So let's look at this. So here I have here's the classic example. So here I have a 0.1 molar solution of acetic acid. Okay? I measure the pH of that, and it's like 3.48. Okay? It's a 0.1 molar solution. Okay? So I'm here. This is acetic acid. That pH is 3. Keep going. 3.82. Okay? So it's a 0.1 molar solution of acetic acid. Now, over here, I have a 0.1 molar solution of hydrochloric acid. Both of them have the exact same molarity of 0.1. This pH is much lower. It's like, keep going. It was like, I think it was initially like 2.43. Okay? Now, here's what you want to visualize. The reason that we measure pH is because it's like a standard. No matter what the acid is, nitric, sulfuric, whatever, we don't build probes for the anions because we'd have to have separate probes for every possible anion to measure that. So this is why we focus on the hydronium ion concentration. So basically that pH probe works by running an electric current in between 2 points, and you measure the resistivity. That goes into an algorithm. A miracle happens, and you get a pH of whatever that is. Okay? So here's what you have to get. Which one of those 2 pHs is an indicator of a higher concentration of hydronium ions? Okay, so listen to me very carefully. You have a pH of 3.82, you have a pH of 2.43. Which one indicates a higher concentration of hydronium ions? The 2.43 or the 3.82? 2.43. Why? Why is it? But it's true. But mathematically, look at it this way.
It's a negative log of a bigger
Ah, right? So, because you're taking the negative log of your hydronium ion concentration, so here's the dichotomy. The smaller the pH, the bigger the concentration of your hydronium ions. Okay? Right? Because if you take the negative log, and here's just a simple example. If I take the negative log of 1.0 times 10 to the negative fourth, oddly enough, I get 4. If I take the negative log of 1.0 times 10 to the negative sixth, I get 6. Okay? So, the higher the concentration, the lower the pH. So, the only way that I can have a lower pH is if more of this has ionized. So, this is the fundamental difference when you get to number 8. If it's a weak acid, when you set up that rice chart, okay, let's say that, here's just a generic way to look at this. If it's a weak acid, let's say that you start at 0.1, and it's a weak acid. Only a certain percentage of that is going to ionize, not very much of it, okay? Only a small percentage of that is going to ionize. But if it's a strong acid, all of it is going to ionize, and that becomes the hydronium ion concentration. So if it's a weak acid, typically maybe 3 to 5% of it is going to ionize. So the concentration of your hydronium ions is going to be much less than the concentration of the acid. But if it's a strong acid, by definition, then the concentration of your hydronium ions becomes the concentration of the acid. Does that help? Okay. We're good? All right. Anything else at all you remotely have a question on? Like, oh, I'm not sure if that's right. Going once. Going twice. Oh, could have gone once. What?
14C and D kind of picked me up. I don't know.
14C and D?
Yeah.
Okay? So, here's the deal. So you had Hockle, right?
Mm-hmm.
True?
Yeah.
And you started off with the 1.5 molar solution, 0, 0. True? Good with that. Minus x, old routine. You assume that subtracting this x doesn't make any difference. Okay? So here's the deal. So you know the Ka value, which is going to be x times x divided by 1.5. So here's the main idea. Once you find that hydronium ion concentration, which should be like 2 times 10 to the negative fourth, that's your hydronium ion concentration, but because it ionized in a 1-to-1 ratio, that's also the concentration of your anion. So your hydronium ion concentration is the same as your anion concentration. So your answers to A and C are the same. Okay? Then on D, it wants the concentration of the acid. Well, the concentration of the acid basically didn't change. That's still 1.5. Okay, so don't make that complicated.
Oh, so just do the molarity?
Yeah. Yeah. That's it. And your pH should make a and GPA.
On 9, the third one.
Huh?
The third one on 9.
Yeah.
Is it pH 4 or pH 3? But why?
Because of the fact that you're finding the conjugate base. Mm-hmm. So on 9, where you have pH 4 plus, mm-hmm. and you want to write the conjugate base, so you're going to try and figure out what you would start with to gain a proton to end up back here.
Oh, okay.
So it's pH 3 because if this takes in a proton, you end up back at pH 4.
And then you add the plus Y.
Because that's what you were given, the pH 4 plus.
Yeah, I just didn't know if I was supposed to take away the plus or take away the plus and the 4. You know what I mean?
Both.
Yeah, both.
Because that's why it just becomes pH 3. Because you're decreasing it by a proton, so that decreases the positive charge by 1.
Okay. And the number of hydrogen by 1.
Yeah,
Does
which is
both.
just basically a proton.
Okay.
Okay, anything else going on? Let's go try solar. What?
So on question 9, on the second one, the
I was about to say, this is the
H2S,
third one.
would that acid lose both of its hydrogens or
This
just
one.
one?
So it just becomes HS minus.
And how do you know that?
Because I would have, otherwise I'd have to tell you that, hey, I want the second conjugate base. So you just assume that it just goes in stages and it just loses the first one. Anything else going on? Let's go try solar. Okay. What? Okay, so here's the next big thing for today. So we figured out kind of how weak acids work. Now we need to figure out how weak bases work, okay? So it's on the opposite side of the coin. So acids are simple. You can generally write it as HA, ionizes into hydronium ions and anions. If you want to put the water in there, if you put the water in, that's technically more correct because of the fact that that's technically reacting with the water molecule, and that's technically H3O plus, okay? So technically, that's more correct, but a lot of times we just shortcut it. Now, when you have a Bronsted-Lowry base, okay, this is not the Arrhenius, this is the Bronsted-Lowry. Remember, this is all about protons, and this was developed in 1923, and the reason that it had to be after 1920 is because that's when we kind of figured out there were electrons, protons, and neutrons. If you look at, for example, here is a physics book from 1902, okay? If you look at the physics book and you go back here to the index, and you try and find the word like electron, doesn't exist. Protons don't exist. Neutrons don't exist. We hadn't found those particles yet. So when you look at the definition of Bronsted-Lowry, because it involves protons, it kind of had to happen after we found protons. Okay? Now the other thing about Bronsted-Lowry's is that the Arrhenius one is like what I call the Chem 1 definition of acids and bases. That only works in liquids, okay? Titrations, which if you did in Chem 2 or Chem 1, those are always liquids. It's a classic one. You have protons, or you have the hydrogens, which is your acids, you have hydroxides, which is the bases, home run deal. But what they figured out is that you can have reactions taking place that involves gases, for example, like ammonia, okay? And that's what we're going to go through. So here's what you already know. You already should be comfortable with Ka, and this is what I'm going to be able to, that's what I'm going to expect you to be able to do on the quiz tomorrow is a Ka calculation. KBs are not going to be on the quiz tomorrow, okay? So don't flip out and go, oh, we have to know that. No, you don't, okay? KBs are not going to be on the quiz. But here's what's going to be different. On a Bronsted-Lowry base, it's a proton acceptor. So what happens is that you put this in water. Now here's the other difference. When you do base reactions, you have to include the water molecule, okay? The water molecule has to be there. It doesn't have to be there on the acids, but it has to be there for the bases. Because basically what happens is that this thing comes along, whatever that base is, if it comes up to the water and goes, yo, sup? Give up the proton. So this is like the lunchroom bully, okay? Comes up to this little freshman in the lunchroom and says, yo, give up your lunch money. So what happens is the water says, fine, take Polly the proton. Really don't care, it's annoying anyway, it's taking, okay? So what's going to happen is that the base is going to gain a proton. So we added H to that. We increase that positive charge by 1. Then what's left over, and this is the most important part, what's left over are hydroxide ions. Okay, so here's the difference. When you have a weak acid, you're generating hydronium ions. When you have a weak base interaction, you're generating hydroxide ions. So what that means is that when you have a weak acid, it lowers the pH because you're generating hydronium ions. When you have a base reaction, you're generating hydroxide ions, so that raises the pH. Okay? So this is going to be important when you look at the rice charts. When you're doing a base, you are generating hydroxide ions, so the water will become more basic. The pH is going to shift to being above 7. So let me kind of give you a classic example. So, and this will all make sense. Don't worry about writing this down. I won't ever expect you to know this, but here's the basic idea. Let me get all this written down and then. Okay. So, here's the story. So let's say that you have ammonium ions. I gave you a solution of ammonium nitrate. Okay? It's a compound, ammonium nitrate. It's white powder. Always entertaining.
Don't forget, I'll have a question for you then.
Okay. So, you would take this ammonium ions, because I can't just give you ammonium ions. It has to be bounded with something else. Typically, it's like ammonium nitrate. It's white powder. Also very explosive.
Oh,
I'm just saying.
do we
It's
have
fertilizer. Huh?
any? Do we have any?
Oh yeah, we got bottles of it.
We should make an explosive.
No. Just because it can doesn't mean it's going to.
Yeah, we
How,
kind
mu-
of.
what
How much
explosive power would you estimate
Guys, I can
approximately?
steal
A lot.
some. Go do my
Yeah, I guys, I
But
know
you
where
have,
it's
but
at.
there, it isn't just throw a match in it. I mean, it's a complex process.
Oh wait, okay, but are we gonna make dynamite soap? We should.
What's
It's a
that?
lot of fun.
We'll see.
I've
So
never
there's
made
the-
dynamite soap.
Okay.
Crystal meth.
So, Skippy,
For
Okay.
scientific purposes only.
no. Okay, so you're going to have ammonium nitrate. You're going to put it in with water. You're going to generate hydronium ions and ammonia. Ammonium is different than ammonia. Ammonium is NH4, ammonia is NH3. This is a neutral molecule. This is a charged ion. Okay? So if you did this reaction, you would see the pH drop. Okay, not significantly, it would drop a little bit because you're going to form some hydronium ions. Okay, so this is one of the things you're going to do in the lab. You're going to do this, you're going to see the pH go down. So if you were to write that Ka expression, it would be, and I included water in here because I want things to cancel out. This is why I included the water. So that's your hydronium ion times your ammonia divided by your NH4. Easy peasy, lemon squeezy, should not be a problem. Now, if you take ammonia, okay, which is a gas, smells very, very pungent, okay, makes your eyes water. You inhale enough of it, it completely messes up your lungs. So if you take ammonia as a gas and bubble that through water, what you will form is NH4, so you're going to form ammonium ions, and you're going to form hydroxides. Because you're forming hydroxides, what you will see is that the solution is going to become basic because you're generating hydroxide ions. So the first reaction is going to make the solution acidic. The second reaction is going to make the solution basic. Okay? Now, because you're dealing with Kb values, it's the same idea. It's always products over reactants. So it's the concentration of my reactants divided by my products. And you will always, there's no variation to that theme. No variation to the theme. It's always products over reactants. Okay? Always. No exceptions. Now, what I'm going to do is I'm going to do a little bit of hocus pocus. I'm going to take Ka and I'm going to multiply that by Kb. Okay? So I'm going to take that H3O plus times NH3 divided by NH4. Then multiply that by NH4 times hydroxides divided by NH3. Now, here's where the magic happens. Notice that your hydronium ions cancel out. Notice that your NH3s cancel out. So the only thing you're left with is your hydronium ion concentration times your hydroxide ion concentration equals 1.0 times 10 to the negative 14th, which also equals Ka times Kb. So here's the significance of this. Ka and Kb are going to be inverses of each other. So because these two numbers multiplied together always have to equal the auto-ionization constant of water. So if something has a very, very small Ka, that means it's going to have a really big Kb. Or if something has a really, really big Ka, it's going to have a really, really, really small Kb value. So this is why when you look at your chart, okay, you're listed Ka values. You don't have to list Kb values because if you have the Ka value, all you have to do to get the Kb value is divide your Ka value into the auto-ionization constant of water. That's why they're not listed. Now, if you look on the if you flip that page 1092, if you flip that over, there's a list of Kb values. You'll notice that the list of Kb values is much smaller than the list of Ka values. Okay? There's a whole bunch of weak acids. There's not very many weak bases. Okay? It's just the nature of the universe. Okay? So there's a whole bunch of Ka values, not very many Kb values. So let me explain how this works. So let's say, for example, we're going to deal with hydrofluoric acid. And that's going to turn into this, right? And the Ka value of this is 6.8 times 10 to the negative 4th. Okay? So, if you look at, and we're going to do a little comparison here, the NH4 has a Ka value of 5.6 times 10 to the negative 10th. Okay? Well, hold on. Okay, so here's what I want you to, here's what you should be able to figure out. The Ka of hydrofluoric acid is 6.8 times 10 to the negative 4th. The Ka of ammonium is 5.6 times 10 to the negative 5th. And this is what this turns into. I should have written that up there, but I didn't feel like erasing it, right? So here's my question. Okay? Which one, and listen to me very carefully, which one is the stronger weak acid? Hydrofluoric or the ammonium ion? Which one is the stronger weak acid?
Hydrofluoric.
Why?
Because its Ka value is bigger.
So what? You're right, but
You
so
said
what?
strong acids either have undefined or really, really big Ka values.
Okay. So fundamentally, look at how you get those numbers. When you look at how you calculate any Ka value, and this is where you have to be able to look at the math. Okay? So this one is 10 to the negative 4th, this is 10 to the negative 10th. So to get 10 to the negative fourth, which is a bigger number than 10 to the negative 10th, to get this bigger value, that means these hydronium ions and those anion concentrations here have to be relatively big, and this has to be relatively small. To generate 10 to the negative 10th, these numbers up here are really, 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 really small. So what that means is that this isn't favored very much at all. You're only going to get 10 to the negative 10. These concentrations here are going to be really, 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 really small, which means this thing isn't going to ionize much at all. This one's going to ionize a lot more. Okay? Got that idea? Now, if you want to find, and we're going to come down here with this one, if I want to find the Kb value of the fluoride ion, okay, so this is what you're going to do in the lab. So what would happen is I would give you like a bottle of sodium fluoride and want to dissolve that in water. So what's going to happen is the fluoride ion is going to be lurking around with the water. And it's going to go up to the water molecule and go, "Sup, mind if I dance with your proton?" The water's going to go, "I don't know, kind of like my proton." Fluoride's going to go, "Come on, man. I'm the conjugate base off of a weak acid." So what's going to happen is that you're going to have the capacity to reform the acid and have some hydroxides left over. Okay? So if you put the fluoride ion in with water, it's going to try and reform that acid because of the fact that it's a weak acid, which means that it really, really, really likes its protons. So, in this situation, I want to find the Kb value of the fluoride ion. It's not listed there, but you have the Ka of hydrofluoric acid. So if I know the Ka of hydrofluoric acid, how can I find the Kb value of the fluoride ion?
Divide it by 1 times 10 to the negative 4.
Yeah. So if I want to find the Kb value of the fluoride ion, somebody take 1.0 times 10 to the negative 14th and divide that by 6.8 times 10 to the negative 4th. What do you get?
1.47 e to the negative 11.
Times 10 to the negative 11th. Now, notice that that Kb value is really, 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 really small. Okay? Now, this is what you want to be able to think through. When you look at how that Kb value is calculated, that's your hydroxide ion concentration times your HF concentration divided by the concentration of your fluoride. So I want to make a really, 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 really small number here. Okay? This is just has to be 10 to the negative 11. Well, so what that means is that these numbers here are going to be really, really small. Okay? So here's the dichotomy. Weak acids, the weaker the acid, okay, the stronger the conjugate base. Because these have to go in opposites of each other. So if you look at hydrofluoric acid, okay, it's a relatively weak base. Excuse me, it's a relatively weak acid because it's 10 to the negative 4th. Which means that it's going to then, when it begins to act as a base, you're going to generate a really, 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 really small number, which means I'm not going to make much of this. So this is the dichotomy. So as an acid becomes more weak, meaning that the Ka values become smaller, the Kb values become bigger. Because if you have a really, really weak base, you can put this in terms of human interaction, okay? You go to prom and you are madly in love. You have found your soulmate, okay? There is a really, 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 really strong attraction between you and your date, okay? Really, really strong attraction. Oh, I love you. Oh, okay? Cool. Happy for you. Which means you're not going to ionize very much. So the stronger the bond between the anion and the proton, the less likely it is to ionize. So the weaker the acid, the stronger the bond between the hydrogen and the anion. However, once you get that anion off by itself, then it's like, oh, I'm not stable. I need to be with my partner. Okay, so then it's going to go up to the water molecule and go, yo, mind if I take your proton? Okay, because to feel complete, I got to have a proton with me. Okay, it's like I can't be single, man. I got to, hey, help me. Okay, water's going to go fine. Quit your whining. Just take a proton. I don't care. But then what's left over is the hydroxide. Now, one last problem, and I'm going to turn you loose. So let's say that you've got this. I want to take NH3 plus water. I want to get NH4 and hydroxide. And this is a 0.15 molar solution. Now, oddly enough, we're going to use rice charts, shocking as that may be. Okay? So, I want to calculate the hydroxide ion concentration and the pH. So this is a little bit more complicated, but it's not bad. Okay, it's just basically we're going to throw in an extra 2 steps. So here's the story. The Kb value of ammonia is 1.6 times 10 to the negative third. Okay, that's your Kb value. Look it up, you can find it, ammonia. So here's the story. It's the same thing. You have a 0.15 molar solution of ammonia. These start off at 0. It's the exact same process. You're going to go minus X, plus X, plus X. This isn't going to change. This becomes 0.15. That becomes X. That becomes X. It's the exact same process. Okay? It is the exact same thing. Do not make this difficult. It's the exact same thing. So then, your Kb, now here's the paradigm shift. Your Kb is your NH4 concentration times your hydroxide ion concentration divided by your NH3 concentration. At equilibrium, because it's the big K. Okay?
That was just funny.
Okay. Okay. It's the K down. Okay. So, here's what's going to be important. This is going to be X, that's going to be X, that's going to be 0.15. Kb is 1.6 times 10 to the negative third. Save some time when you do this. You get, your X values are 1.6 times 10 to the negative third. Okay, that isn't the Kb value. I don't remember what the Kb value is. But when you do this, you get an X value of 1.6 times 10 to the negative third. I looked at the wrong number. You have to look up the Kb value. But here's the important part of the story. When you find X, that's your hydroxide ion concentration. That is not your hydronium ion concentration. That's your hydroxide ion concentration. So, what you can find is the POH by taking the negative log of 1.6 times 10 to the negative third. Okay, so somebody do that. I don't have these numbers here. So somebody take the negative log of 1.6 times 10 to the negative third.
2.795.
So call it 2.7. So call it 2.80. Okay, that's your POH. So how are you going to get your pH?
Subtract it from 14.
Subtract that from 14. So if you take 14 minus 2.80, you should get 11.20. There's your pH. Because it's basic, because you're generating hydroxide ions. The pH is above 7. See? It all kind of makes sense. Okay, so all of these are out of your book, okay? Can you what? Huh?
Can I go check out a book?
That would probably be a good idea, Skippy.
I'd agree.
How'd you do the questions yesterday?
I just asked Catherine. Oh wait, I did the questions for the textbook in Encore.
He used my textbook.
And also, when I looked up the Ka value, all of the ones that I looked up, the certificate for the textbook were wrong. So I have to redo those problems.
What did you do?
When it said like get the Ka value from the textbook, I just looked up the Ka value and every single one of them was wrong. So,
Well,
tough.
For you.
Yeah.
Okay, there you go. When you get to 79 and 80, only do A.
oh, that's
It's just, that's. You know, parts A through I.
I'm going to create a map.
And when in doubt,
one of them's gonna be A.
I'm going to say the R word.
Like A through J.
You might read the chapter. I'm just saying, it's the R word.
Is that it?
That's it.